Okay, this is college algebra, and we're going to finish up quadratic models today. Today we're going to talk about a perfect quadratic model, and this is a pretty typical type of quadratic model. It's projectile motion, and we're going to associate this quadratic equation with second differences. I'll talk about what that means. So recall that when changes in input are constant, the first differences of the output are constant or nearly constant with a linear model. So if I were given some linear model, okay, let's say that my x values, actually, yeah, this way. Let's say that my x values are 1, 2, 3, 4, and my y's are 3, 9, 15, and 21. Okay, so between 3 and 9 is 6, between 9 and 15 is 6, between 15 and 21 is 6. So these are called first differences. So what I've essentially done is I've taken 9 minus 3, then 15 minus 9, then 21 minus 15. If I were to graph this, I would get a linear function with the slope of 6. For a quadratic function, my first differences for the linear function were constant. In a quadratic function, the second differences will be constant. Okay, so let's calculate the first differences of this rocket equation. So we've got 117.6 minus 68.6. Okay, so that's 49. 147 minus 117.6 is 29.4. 156.8 minus 147 is 9.8. 147 minus 156.8 is negative 9.8. 117.6 minus 147 is negative 29.4, and 68.6 minus 117.6 is negative 49. Okay, so those are my first differences. All right, let's go to the second differences. So I'm going to do this subtraction again with the first differences. 29.4 minus 49 is negative 19.6. 9.8 minus 29.4 is negative 19.6. 9.9, I'm sorry, negative 9.9 minus 9.8. Uh-oh. 147 minus 56.8. This should be 9.8. Negative 9.8 minus 9.8 is negative 19.6. Negative 29.4 minus a negative 9.8 is negative 19.6. Can you guess? Negative 19.6 is the last one. All right, so my second differences are constant. Okay, when second differences are constant, that means that it's going to be a quadratic equation. Okay, if the third differences, so if the second differences weren't constant and I went to third differences, if those were constant, then I would have a cubic equation. So let's determine the quadratic equation from these data. So I'm going to enter stat, edit. My L1 is 1 through 7. and the height, my L2 is the height of the rocket in meters. Take a moment to enter those into L1 and L2. Stat calc quad reg vars y bars function. I'm entering it into y1, and look at my r value. It's 1. So that means this is a perfect quadratic equation. It goes through the data perfectly, and the equation is y is equal to negative 9.8 x squared plus 78.4. Okay, and my and my c is 0. Okay, let's see what this graph looks like. Zoom 9. Okay, check that out. If I were to do a linear regression equation, okay, with this data, it wouldn't work, okay? So let's check it out. Second calc linear regression. This linear regression yields, okay, y is equal to 117.6. If I were to store this into y2, okay, you can see the constant going straight across, okay? Oops, where did it go? Let's just enter it, 117.6. There it is, okay? It just cuts the graph in half. So you can see that a linear equation definitely would not be anywhere close to this. So comparing it to the quadratic, you see, doesn't work. Okay. All right, we're going to do something called interpolating. So what that means is that we're going to take some data and we're going to, the interpolation means that it's inside or in between the data. So we're going to do some estimating using our model, okay, but going in between. So 6.5 is between 6 and 7. So what is the height of the rocket at 6.5 seconds? Second calc value. .5, and the height of my rocket is 95.55 meters. Okay, what is it 3.5 seconds later? Second calc value, 3.5, and it looks like it's 154.35 meters. Now we're going to extrapolate the data, so that means we're going to go beyond the data. So we're going to use the model to estimate this information beyond the data. So 8 is beyond the data that we have, and we want to know the height of the rocket after 8 seconds. So second calc value 8. I'm going to have to adjust my window. So let's let our y min be 0. Okay, I'm also going to need to extend my x max. Let's let it be 8.5. So again, my window I had to adjust. I'm letting my x be 0.4 to 8.5, and my y to being 0 to 171.794. I think the calculator came up with that. Okay, so second calc value 8. After 8 seconds, this thing is landing. Okay, so I get 0. So 8 seconds is when it lands.